Alright, we are finding the velocity halfway down our first descent. To do this, we are going to be using two equations. One for potential energy, which is mass times gravity times height, and one for kinetic energy, half mass velocity squared. The potential energy for the marble in a roller coaster as it's at the top or just at the start of the hill is represented through its mass, 0.005 kilograms, times the force acceleration due to gravity, which is 9.8 meters a second, times the height, which is 1.9 meters. When you calculate that out, you get 0.0931 joules. And that's the potential energy from the top of the roller coaster, or top of the first descent, to the bottom of the roller coaster. So we're going to want to be able to find from the top of the roller coaster down to the bottom of the first descent. So to do that, we're going to use our second potential energy equation, and we're going to take basically the same equation except change around what our height is, because at the bottom of the first descent it's 1.44 meters high, and so that changes our potential energies around a little bit. And when you calculate that out, you get 0.07056 joules, which is less than when it was at the top of the hill, because now it's just down the first descent, and since it has less height or less position, it has less potential energy and it has a greater kinetic energy. And that's something that we're going to be calculating. So the reason we calculated both of these potential energies is in the law of conservation of energy, it says that a loss in potential energy is equal to a gain in kinetic energy. And so if we can calculate from the top of the descent to the bottom of the descent, if we can calculate the difference between those two potential energies by subtracting them out, as shown on screen, we can then use that and hypothesize that at the bottom of the first descent, not halfway, at the bottom of the first descent, we can hypothesize that that is indeed our kinetic energy. Now, because we're trying to go halfway down the first descent, we would then need to divide that in half, as I'm showing on screen right now. We're doing half. So you divide that by 2 or multiply it by 1/2, and in the end you get a kinetic energy for halfway down the descent of 0.01127 joules. And I'm just going through how that's the kinetic energy right now. So now I'm writing out what I said previously of how the loss in PE with no friction. That's an important part of this. If friction is present, then you have to add in the force of friction, and your calculations get quite more complicated. But with no friction, your loss in potential energy equals a gain in kinetic energy. And then right now I'm just plugging that potential energy I got on top into my kinetic energy equation. From here on to the bottom of solving the problem, it's more algebra and just plugging in the numbers to get to the bottom. The important conceptual concept that you need to know is that potential energy is equal to kinetic energy. So like a loss in potential energy is equal to a gain in kinetic energy. So right now I'm multiplying those out on screen. I have my mass, which is 0.005 times 1/2 v squared, which is the equation for kinetic energy. When you multiply that out, that's 0.0025 v squared equals my 0.01127 divided by 0.0025, and you get 4.508, excuse me, equals v squared. The important part of that is it's not velocity, it's velocity squared. That's really important part of it, because if you just stop right here, your velocity is going to be very high, especially when you start to get into larger and larger numbers, because 4 meters a second is very fast for that marble to be going. So that's why you take the square root, and approximately at the end, halfway down the first descent, the marble should be going approximately 2.1232 meters a second. That, of course, is far from reality, because in reality there's friction, there's some minor air resistance, and both of those things take away from the problem. Yeah. Right now